All right, Pan, go ahead.
Greetings. It's my pleasure to introduce today's applicant, Dr. Sam Courville. It's a little known fact that Sam is one of the founders of the Colorado PSI office. Um, Sam was on an internship with me at the Southwest Research Institute when I transitioned over to PSI and we opened the office here. Sam actually had the joy to work in my basement for a week or two while we were making that transition from Swery. Um, so I'm very excited to learn more about what Sam's been up to the last few years. So without further ado, Sam, please take it away.
Well, thanks, Dan, for the introduction. Yeah, that is pretty funny. I was thinking about that earlier today. So I've been sort of involved with PSI for almost 10 years now. That internship started in 2016 when I was still an undergrad. And then I sort of rose through the ranks. Was a research assistant, then associate, worked with Fan at PSI Colorado, interpreting Mars radar, part of the subsurface water ice mapping project. Worked with Deborah on some lunar photometry, and then also with Gareth and Than and Matt, some geophysical instrument design for the moon and Mars. I'd love to talk about all of those more, but today I'm going to focus on the things that I haven't done with anyone at PSI. The stuff that I did, the stuff I've been focusing on for the last 5 years during my PhD. I got my PhD back in May of this year. All about the interiors of planetesimals, asteroids, and dwarf planets. This is work that I did at Arizona State University, where I got my PhD. A lot of it funded by NASA's Psyche mission, and a lot of it done at JPL over a few summer internships. So I don't think I need to tell anyone at PSI why you should care about small bodies in the solar system, but I can say the philosophy that's sort of driving my interest in the investigation of these bodies. If we think about the questions, how do planets form? How did we get here? How did life originate? Earth is kind of a bad place to think about these big picture questions like this. Even though it's the only planet we know of with life, the one we've grown most accustomed to, it's quite complicated. Most of the information on our origin has been lost, complicated by tons of processes. And so it's really these small bodies throughout the solar system that are preserving information about planetary formation and our origins. So what do I mean by, or what specifically do I mean by, or what do I want to focus on? Really what I'm interested in are when what I consider to be interesting geological processes begin. You can sort of jokingly map geologic complexity over time on solid bodies as solids condense from the nebula into a protoplanetary disk and then accrete into the first solid planetary objects, planetesimals, which then combine and grow into protoplanets and onward. I'm interested in sort of this segment, this uptick right here, where we're getting the first spherical bodies, small bodies, with the most primitive compositions and undergoing the first major interior geological processes. Those processes are sort of something like this. Imagine a planetesimal forming at the beginning of the solar system. It accretes a cold mix of rock and ice The exact composition and the abundance of volatiles depends on where it forms in the protoplanetary disk. But then it begins to heat in its interior from radioactive isotopes. At the beginning of the solar system, aluminum-26 is the radioisotope that did most of the heating. It has a short half-life of just 0.7 million years. So all of it every atom of aluminum-26 is gone by today. But in the first 5 million years ago, the first 5 million years of the solar system, that was driving a lot of heating within planetary interiors. But then longer-lived radioisotopes like potassium-40 could keep some of these interiors warm billions of years later. So as the planetesimal heats, sort of the first major interior milestone is when volatiles melt. For example, water at 0 degrees C, when it melts, the water will, depending on the interior model, depending on the aspects of the interior, could migrate outward from the interior, forming an ice shell perhaps, and also hydrating the silicate interior. As heating continues, a few hundred degrees Celsius, then we can start metamorphosing the interior, changing the composition of the interior, dehydrating some of the silicates, perhaps releasing volatiles again. Continue heating it more, 1,000 degrees Celsius or more, then we're talking about melting the silicate interior. That's where we can form an iron core. And so the exact extent, the exact behavior, the amount of circulation of these processes depends on the specific body in question. But these are the general steps in planetesimal evolution. And it's the amount of heating that determines where this chain stops. So for the rest of this talk, I'm going to go over 2 case studies from my recent published work. I'm going to talk about the asteroid Psyche, which is potentially an exposed metal core of a protoplanet. And I'm going to talk about Ceres, the dwarf planet in the asteroid belt, and how it may have all the ingredients necessary for life. So, as I mentioned, a bunch of my PhD work was with the Psyche mission. The Psyche mission is on its way to the asteroid Psyche. In May, it's going to do a flyby of Mars, get a gravity assist, and head out to the asteroid belt where it will arrive at Psyche in 2029. If you haven't thought about the mission very much, you may know of Psyche from some of the silly headlines that occasionally make it to the news. The $10 quadrillion asteroid. This comes from the fact that if Psyche is a metal-rich asteroid, everyone's interested in potentially mining it for precious metals, which I think is terribly silly. Trying to bring anything worth that much back would make no sense. And then it's also silly because we don't know what Psyche is yet. We don't know that it is an exposed metal core. The mission is headed there to find out. This is our current best image of the asteroid. It's a space potato. It's got some dimples. It's oval shaped, so it's probably a collisionally evolved asteroid. Has been hit by some large impacts. What else we know? We have estimates of its density, about 4 grams per cc. So that means it's definitely not entirely metallic iron. If it was entirely metallic iron, it'd have to be much more dense than that. But it's also too dense to be primitive meteorite-like composition. So it's certainly a mix of metal and silicates. And the degree of porosity probably determines how much metal Psyche has, and also how pure the metal is, if it's pure metallic iron or if it's iron sulfide, for example. The other thing we know is that its surface appears heterogeneous. This is a map of the dielectric constant over Psyche's surface from the ALMA radio telescope. And metal has a much higher dielectric constant than silicate rocks. So these values, these best fit values from the surface of Psyche, suggest that it has patches of metal-rich regions on the surface. So now what we're looking for are hypotheses that can explain a dense asteroid with patches of metal on the surface. One clear one is that, oh, it's a planetesimal that formed a metal core and then had impacts that disrupted it, exposing some of the metal and stripping some of the silicates away. That's certainly a hypothesis. I'm going to focus on a more fun one today called ferrovolcanism. This hypothesis, this hypothetical process, could occur on planetesimals that form an iron core. And then as the iron core solidifies, pockets of that melt gets trapped and pressurized and forces its way upward, intruding into the mantle, possibly erupting onto the surface. And so that could explain the metal patches on the surface observed for Psyche. Now, as I said, this is one potential hypothesis. We don't know what Psyche is. And so in this talk, I'm going to focus on this specific hypothesis, explain a model of how it works, and then describe the observations that you would want to make to determine if this hypothesis is true or not. And of course, we need to do this for all the hypotheses we can think of so that when the Psyche mission arrives and we actually get measurements, we can choose, we can ask the right questions to figure out which hypothesis is most correct. The actual goal of the mission, or one of the objectives, is simply to determine if Psyche is a core or a remnant of a core. And so in this particular ferrovolcanism model, that story would look something like this. Psyche accretes, begins heating, forming a core. Later on, that core begins to solidify. Now I have these blue lines. So as the core solidifies, it could generate a magnetic field. Solidifying metal core with motion of the molten fluid would generate a magnetic field, just like how Earth generates a magnetic field in its core. Then as the core begins to solidify and molten material gets trapped and forces its way upward, we could have intrusions and eruptions of this molten melt forcing its way upwards. And then later on, when the core is completely solidified, remnants of that magnetic field could be locked away in these metal-rich dikes that have intruded upward. And so at present day, what we'd want to look for are exposures of metal on the surface and associated remnant magnetic fields. I'm going to break down this model into more detail now. So we'll step through this again, one step at a time. This is proto-Psyche. After it's formed its molten core, it's heated enough to melt its interior. And in this model, I'm going to say its molten core is made of iron and sulfur. In reality, there would be other metals too in the core, but this simplified model just treats iron and sulfur. And it melted from the heating of aluminum-26 at just a couple million years after the beginning of the solar system. Um, and now this is how the interior temperature of the body would evolve over the next tens of millions of years. So on this plot, the bottom axis is time after the core formed, with the right edge of the plot, about 45 million years, being when the core completely solidified. And then on the vertical axis is depth within the interior. So the bottom is the center of Psyche, and the top is the surface of Psyche. So the shaded region here shows where the molten core is and how it solidifies over time. In this model, the core solidifies inwardly. There's a lot of research, and it's unclear what the actual direction would be in reality. So there's lots of fascinating research on how core solidification would occur on planetesimals. But okay, in this model, as the core solidifies inwardly, the first thing that solidifies is pure iron. Pure iron solidifies, and that means the remaining molten core becomes enriched in sulfur. So that's this red line. It starts with less sulfur in the core and ends with higher sulfur in the core, until it reaches the eutectic point where both iron and iron sulfide solidify, and then the composition of the core doesn't change anymore. And that's important because if we have dendritic core solidification, so that's where the core is solidifying from the outside in, but also because of the low gravity environment, it's not the solid iron, which is most dense, is not falling into the interior. Instead, it's building up and then trapping pockets of melt because Psyche is an odd shape. These pockets become more pressurized. As they enrich in sulfur, the density of the fluid goes down. Their volume wants to increase, but they're trapped. So that is what builds up pressure, especially also since the iron solidifying around it is more dense than the fluid. So there's buoyancy and pressure in those pockets, and that's what could drive the eruption of metal from the interior of a solidifying planetesimal into the rocky mantle, possibly up to the surface. You can kind of think of it like an iceberg, basically, where the height of the eruption height is determined also by how much is underneath. Right. So now, by tracking the composition of the core and the temperature of the core, I can estimate the height at which these dikes would intrude upward into the rocky mantle. And so the dikes could reach the surface before the core is entirely solidified. Now, the other cool part about this process is that while the core is solidifying and generating a magnetic field, these dikes would be erupting, reaching colder temperatures, where they eventually solidify at or near the surface. And so if they reach high enough or shallow enough depths, they'd be able to cool off and solidify below the Curie points of various minerals. So that means when they erupt high enough, they could acquire remnant magnetization, recording a snapshot of the magnetic field that the asteroid, that the planetesimal created during core solidification. Psyche, the spacecraft, has a magnetometer, and we'll be measuring magnetic fields. So then the question becomes, could these remnant fields associated with ferrovolcanism be detectable? So that's what this plot shows. On the bottom axis is the height of the dike within the interior, and there are three lines here for different dike widths. And then the vertical axis is the magnetic field strength that you would expect at the orbital altitude of the spacecraft. And that's the approximate detection threshold. So if you have dikes that are about, or dike swarms, right, total magnetized area, so it's not strictly speaking the dike itself. The magnetized region is about 1 kilometer wide, then it would be detectable. That would be about 0.5% of the core volume. So if you have 10 or so of these events around, that would be about 5% of the core volume. So finally, for this hypothesis, this is sort of what we can put together like a detection matrix of what observations would suggest that this hypothesis were true. So if we see localized sulfur-rich metal on the surface of Psyche that appear to be like eruptive deposits, and there are corresponding magnetic anomalies, that would be a strong indicator of a process like ferrovolcanism. However, we know that Psyche is a collisionally evolved world. We can tell from the images that exist that they're definitely large impact basins. So any geomorphological evidence of volcanic type features may long have been erased. In that case, we'd still would expect to see metal scattered over the surface, perhaps large exposed regions of metal, sulfur-rich, also associated with crustal magnetic anomalies. Now, the magnetic anomalies may not be present, though, either for a litany of reasons. The dikes could be too small, the dynamo and the mineralogy is wrong, or there was no core dynamo during core solidification. So that doesn't necessarily mean there was no ferrovolcanism, there was no magnetization. If you don't really see anything, though, it's still inconclusive because there could be these ferrovolcanic dikes buried in the subsurface that aren't visible, but it's likely not. So this is a recent paper that I published, and the author list is here. And of course, I want to thank all my collaborators in the Psyche mission. As I said, this is one potential hypothesis for the asteroid, and I think it would be the coolest. So I'm really excited to see what the Psyche mission observes when it gets there. But I just want to also keep minds open that there are many other hypotheses for the asteroid itself. Specifically, I'm most excited, not in 2029, but even later, as the Psyche spacecraft works its way down from its first reconnaissance orbit down to its closest orbital approaches. That's when the best magnetometer data will be captured. The closer the spacecraft is to the body, the stronger the magnetic field it can record. So I'm particularly excited to get some magnetic measurements from that close up, see if there's a magnetic field and what it can tell us about the interior. So I hope to be a participating scientist when that call is eventually released in a few years from now. So actually, I'll pause there before I jump into Ceres if anyone has questions about that research. And if not, I'll keep going. I'll give a couple seconds.
Hey Sam.
Hey, Gareth.
Yeah, really, really cool study. Thanks for sharing that. So, this is really neat. It kind of reminds me the type of volcanism about the way people try to describe how dike emplacement on the moon to get through the an orthocytic crust, and the
Yeah.
density issues you have there. Of course, with an asteroid like this, so you're constrained with this happening within what the first 40 million years. Was that the axis on the x-axis, the volume?
Yeah, exactly. It would be the first couple tens of millions of years is when the heating, when core solidification would be occurring.
Got you right. So you got this narrow window, right, where this sort of like ferric volcanism can happen. And then I guess you're up against the survivability, right, of like heavy bombardment during that time as well, I guess.
Right. So the other
Yeah,
thing I didn't quite uh, capture is, yeah, the impact processes that are also occurring at this time. We don't know, right? It's tough. It's all stochastic. It's random. What level of
right,
impacts did Psyche have? It's very possible to create an asteroid that's denser than the average asteroid. You actually need to strip away some material. So you need to
right.
differentiate it and then strip away some of the silicates at the top. Um, so that implies that, unless Psyche has some weird origin that miraculously formed with a metal-rich composition, right? There are a few meteorite classes that indicate as a possibility. Um, but unless, well, so Psyche likely had to experience some level, at least one, possibly multiple impacts to remove material. And so there are lots of different hypotheses about impacts. Some completely destroy the body and then it comes back together and it could still then be hot enough to have a core. Some are more just like stripping events. Um, these are all things, all hypotheses that are going into the master plan of observations for the spacecraft to make when it gets there.
Yeah, cool. That's really exciting. I'm really looking forward to these results. Yeah, thanks.
This is just the hypothesis that I really want to be the case because I just think
Fair
it's
enough. Yeah, sounds a good one.
it's
I like
super
it.
cool. All right, I'll go ahead and move on to the second part then. Um, Ceres, another object in the asteroid belt. um, uh, the largest object in the asteroid belt, Ceres, actually a dwarf planet. Um, Unlike Psyche. Now we're talking about uh, what I like to think of as a primitive, really a relict planetesimal from the early solar system. It does not appear to have been disrupted catastrophically, and its composition appears to be pretty primitive, carbonaceous chondrite-like. So perhaps its bulk composition is a certain amount of water, rock, and then that primitive organic material that's found in carbonaceous chondrites. Um, so that has led, excuse me, interior modelers to suggest that its interior is something like this. There's an ice-rich uh, uh, crust, a hydrated rocky interior, and perhaps a layer of brine, a layer of water between, or just brine within pore space within the rocky interior. Um, and this brings up an interesting question because, you look at Ceres, it just looks like just another cold, dead gray rock in the asteroid belt. Um, but if we think about it this way, it's starting to put together a picture of the ingredients for life. If Certainly the surface, near the surface, is not habitable. But as you go deeper and it gets warmer, there could be conditions for liquid water. And based on the composition of carbonaceous chondrite meteorites, and if that's similar material to the interior of Ceres, we know that it's got plenty of the right elements. Um, uh, the amount of water and the amount of organic molecules is orders of magnitude more within Ceres per volume than Earth, for example. A better question might be whether or not Ceres has um, energy, chemical energy that could support life. Energy, just like us, needs food, or microbes, just like us, need energy to live. They need food, something to eat. On Ceres, that would be in the form of chemical energy from exploiting chemical reactions that are at disequilibrium. Then the other thing is we may need time. There may need to be a sustained habitable environment with energy for many millions to billion years for life to arise. So I'm not suggesting Ceres has life, but more that it may have all the ingredients, which is then fascinating because then what's missing? Lots of times when we talk about life on ocean worlds or bodies that may have liquid water in their interiors. This is a picture that is conjured, a seafloor hydrothermal vent where hot water from the deeper interior is released into a colder ocean of water. These are great environments for microbes, buffets for microbes, because they bring two fluids that are chemically disequilibrated together. For example, a reduced fluid from the interior, and then the microbes can take advantage of the electron transfer from a reduced compound in the fluid to an oxidized compound in the ocean. These vents, of course, on Earth often rely on volcanism in the seafloor, something to drive convective fluid flow in the subsurface and really heat the fluid quite a lot. Is that something that could occur on a Ceres-like body? So this is going to be another thermal evolution plot of an interior. So this is, on the bottom axis is time again. The left is when Ceres formed at the beginning of the solar system. And at the right is present day. This is log scale. So 10 to the 3 there is 1 billion years after formation. On the vertical axis is radius within Ceres. So this bottom is Ceres' core, and the top is the surface of Ceres. So in this model, based on Ceres' size and its composition and its density, this is sort of a guess at what its interior temperature could be over time. And so in this model, at about 1 billion years later, so again, this would be from long-lived radioisotopes like potassium-40, we reach a peak temperature a little over 500 degrees Celsius. There's an ice shell. Again, this model assumes that the water ice differentiated from the interior, forming sort of an ice-rich shell on the exterior. But then there may be a porosity, liquid water and pore space in the mantle as well. Now, this thermal model, though, predicts a peak temperature in the interior. And that temperature is nowhere near hot enough to melt silicates. So there's not going to be anything like volcanism here. So that picture I showed you, get that out of your mind. That's not what we're thinking about for this interior of Ceres. But that doesn't mean the story's over, because it still is hot enough to induce some mineral changes within Ceres' interior. So this is now tracking a plausible mineral assemblage for Ceres, the core of Ceres. As time progresses and its interior heats up, the big thing is that silicates that may have started hydrated dehydrate. And so that means that there is a flux of fluid from the interior outward. If the porosity and permeability structure of Ceres was allowing, then you would totally have a flux of fluid, a flow of fluid from the interior outward. So this could still power some global fluid disequilibrium, because fluid released from the hotter interior would have a different equilibrated composition of dissolved solutes than fluids in the shallower area. So in this plot, assuming the specific reaction, CO2 and hydrogen, converting it to methane, what was I going to say? In the this particular reaction among these solutes dissolved in liquid water, at deeper depths where it's hotter, thermodynamics favors the CO2 and hydrogen dissolved. At the shallower depths, it favors methane. So if you mix fluids from the deeper interior with the shallow interior, there would be chemical disequilibrium and potential energy to be exploited. So finally, I can what's the word I'm searching for? So finally, I can calculate the energy that would be available based on the amount of fluid that could be released and the extent of chemical disequilibrium, and when and where that would occur within a body like Ceres. And so it's really between about 500 million years after formation and 2 billion years, where the temperature within Ceres could support this fluid flow from the deep interior that could provide a sustained source of energy. And what that means is that we're starting to put together all the ingredients necessary. So this, of course, is another model. This is another a case of a possible interior model. We don't know how hot Ceres' interior was, and hopefully future exploration will be able to constrain that. And that can really help us figure out, well, did this happen? Was there a warmer interior that could supply chemical disequilibrium, or was there not? If there was, that's fascinating, because then we have almost all the ingredients we need. So what's missing? What chain is not being met for the ingredients for life? Another aspect that I didn't touch on, I focused on just one potential chemical reaction, one known microbial metabolism, methanogenesis. But another thing to think about is all the other potential chemical processes that could be happening in this subsurface thermal gradient. So, as I mentioned, Ceres has organic matter, the insoluble organic matter in carbonaceous chondrite meteorites is likely what it is. These are large, big organic molecules, and they break down at higher temperatures, breaking into smaller pieces, volatiles that could also migrate upwards. So that's another source of chemical disequilibrium, another source of organic chemistry that could be occurring in the interiors of bodies like this. In a very underexplored area that I'll be writing a bunch of proposals about. And then, of course, I focus this on Ceres, but there are lots of other small bodies like Ceres in the outer solar system, the small moons or the large moons around Uranus, Kuiper Belt objects, the more classical ocean worlds around Jupiter and Saturn. All of these bodies could be having similar processes. But it all depends on figuring out exactly what's going on in the interior, the max temperatures, and how fluid is moving. So as this work was published also this year, so I thank my co-authors and JPL. So to sum up what I've shown today, core metamorphism of volatile-rich bodies like Ceres could drive their habitability. And the remnant magnetization of the asteroid Psyche could reveal whether or not it has some exciting core formation processes. And it's really future geophysical measurements combined with surface observations that's going to allow us to test these exciting hypotheses. And so that's exactly what I hope to be involved with throughout my future planetary science career. I'm going to maintain involvement with the Psyche mission, and then also I'm trying to get help the effort to make a Ceres sample return possible. This is a mission that would go to one of the bright spots on Ceres, which is possibly evaporites from fluid in the deep interior. it's a high priority in the decadal survey, so hopefully that'll be a future mission, which I hope to be involved in. Um, and with that, I'll take any other questions.
Excellent work, Sam. Thanks for taking us through all of that.
Yeah, it's fun stuff, a lot different than what I've been used to do at PSI.
Absolutely. Um, it's it's great to see the diverse range of things that you're doing. I know there is a running theme of modeling, though.
Yeah, so right, the right, the story changes, but the
Mhm.
underlying expertise is geophysical and geodynamical
Mhm.
modeling of interiors. A lot of it is thermal modeling, but also geophysical measurements.
Do others have some more questions for Sam? If so, speak up or put a question in the chat.
Stunned silence.
Mhm. In your current postdoc, are you working predominantly on the Psyche
Yep.
effort, or is there other aspects?
Yeah, predominantly Psyche. So
Mhm.
it's my focus again is primarily on the magnetometry side of things. We've never actually detected a magnetic field around an asteroid before.
Mhm.
There's been a few missions that can either directly or there's really only been one mission that directly had a magnetometer that could try to measure something from an asteroid, and it did not record one.
Mhm.
That was
So
not a
how
metal-rich asteroid. So this is going to be exciting. This is going to be the first time where we have a mission that orbits really closely to an asteroid. Uh, that
how close is it getting?
I think roughly about half the radius of Psyche, so like 70 something kilometers.
Okay.
That's all. Yeah.
Do you know how difficult it is to maintain that orbit?
Yeah, that's why it's starting in an out, like that's why it's
Mhm.
working its way in.
Uh,
The spacecraft is it's solar electric propulsion, so like Dawn.
right.
And so it's going to arrive, right? So with that such low propulsion power, uh, you know,
Capability.
yeah, is, orbital insertion is really like a really long process that occurs, just sort of gradually
Yeah.
approaches Psyche and is the bounds of when it's in orbit and when it isn't is kind of nebulous. It's interesting to think
Right.
about.
Right. Okay.
But then it starts far outside and it's going to work its way in precisely to figure out the gravity field and then help
Mhm.
determine how close they can actually get. And then you might notice that it actually rotates too, so that orbit, starts going around, but then
Mhm.
those closest orbits were flipped so that they
Yeah.
were polar. And that has to do with the fact that Psyche is rotating on its side, so
Mhm.
um, it's a uh, so that means there are times in its orbit around the sun where one side is entirely in shadow all the time. And
Mhm.
so there are times uh, when the spacecraft arrives, there's going to be one side that we can't see, and then when it ends, there's going to be one side that we can't see. And so the polar orbit actually wants to be done when we can see all sides.
Right. What happens at the end of mission?
Oh, that's a good question. I forget what's. Um, I'll have to ask. Uh, I
You're
don't
not going to
remember.
land, are you?
Yeah, might be a kind word for it. Rapid
It's called litho
planned
braking.
disassembly. Yeah, litho braking.
We've done it at Mars several times now.
I don't know if it's going to be, I don't know what the time scale of crashing it into the surface is.
Do you know if that's the plan or if it's going to try to move away?
I It's going to stay. Psyche is its final resting place.
Okay,
It's not going anywhere else. Just a question of whether how deliberate and how close we're going to get before crashing it.
sure.
Whether it's going to be monitored when it crashes. I don't know. I need to go look at the exact end of life plan. But I mean, if the spacecraft's healthy, I wouldn't be surprised if they try to keep it in orbit as long as possible.
Certainly. Okay, any other questions, discussion? If not, I'll turn things back over to Matt.